Hi everyone, and welcome to the short standalone video that I wanted to make about laws of large numbers. It's going to be about the interaction between measure theory and probability, and it'll illustrate some basic principles and proofs that pertain to this area. I'll try to keep it as self-contained and informal as possible, and I really just wanted to make this video to break out of my video making slump. And I have two series that I'm currently working on, one extended series in differential topology and another mini-series on the prime number theorem, which illustrate beautiful phenomena in complex analysis, but those are slightly longer term. So for now, I just wanted to upload this. First, I want to show that the notion of convergence in measure, which is a rather weak form of convergence that appears in, well, measure theory, is actually quite a natural mode of convergence in probability. So let's consider the binary digits of some number x equals 0 points, and let's index these, etc., where xi are either 0 or 1. And this is going to be in the interval. We use this as a model for an infinite sequence of coin flips. Okay. Now let's define these functions f sub I from 0, 1, where we're thinking of elements in the domain by their binary representations as above. And it's going to map to the two-element set -1, 1. And this is meant to be a heads or tails space, basically. So let's, without loss of generality, let this be heads, let this be tails. Okay, and we're going to say that it sends x to 1 if xi is equal to 1, and it sends it to -1 if xi is equal to 0. Okay, so these functions that basically measure whether the ith coin flip was heads or tails, and it weights each of these as +1 or -1. So taking values in this two-element set accordingly. Then the integral of fi, equals 0 for all I, right? And more importantly, due to the independence of these coin flips, integrals of distinct products are going to evaluate to 0. So this is another way to rephrase the independence of these coin tosses, or the fact that none of these xi depend on other xj. Okay, so now we're going to represent these weighted partial sums. So on average, what is the result going to be? And we set this question up by defining the arithmetic mean of these partial sums. Let's say I equals 1 to n of fi of x. Okay? And the weak law of large numbers says that as n grows large, there's a high probability, which I'll formalize in a second, how we make this precise, that this Sn is close to 0. That is, the values +1 and -1 are roughly equidistributed. So the weak law of large numbers I'll call this the WLLN, in contrast to the strong law of large numbers, which I'll introduce in bit after we prove this. So intuitively, as n grows large, Sn will be close to 0. That is, half the digits of x are going to be 1s and the other half are 0s if they are randomly chosen. And more precisely, this is where convergence in measure comes in. For any epsilon greater than 0, we've got that the probability that, let's say, absolute value of Sn is greater than epsilon goes to 0. All right, so we can choose epsilon arbitrarily small, and the probability that this is greater than epsilon actually goes to 0, which shows that in some sense, Sn is going to be about 0 as n grows large, the number of trials increases, or the number of digits that we look at. So this is convergence in measure. Convergence in measure. Okay. Let's give a proof, which I think is quite illustrative and beautiful. It relies on a vital fact that is interesting in its own right, which is Chebyshev's inequality. Chebyshev inequality. And I'll state one version of it, or at least the version that's just as strong as we need, maybe not the most general. Let f from R to R be square integrable. Let's say, by this I mean f is in L2 of R with respect to Lebesgue measure. Then the Lebesgue measure, which I'll denote by m, the measure of all x such that f of x exceeds epsilon is at most 1 over epsilon squared times integral of, sorry, this is r f squared dm. Okay, so this is not super difficult to prove. I'll leave this to you, and there are more general formulations, but this is the version we need for L2 functions in this case. Now, because the xi are independent coin flips, we can formulate the following. Let's say partial sum from I to n, fi whole squared dm. We can pull this out. Sum 1 to n integral fi squared. And of course, these things squaring to 1, right? All of these integrals are going to yield 1, and then you're just adding these up from 1 to n. So this is just going to be n. Okay? So this shows that the integral of all these Sn squared is equal to 1 over n. So by Chebyshev's inequality, which I'll star like this, the measure of the set of all x, such that now the functions in question, Sn is going to take the role of our f, absolute value of this guy is bounded above by epsilon is at most 1 over n from this above estimate times, not estimate, I mean above calculation, times epsilon squared from Chebyshev. Right, and because this is O of 1 over n, this goes to 0 as n grows to infinity. So this formalizes the weak law of large numbers. Yeah, I think this is an elegant proof that exploits why independence is necessary. It uses this nice integral estimate in the form of Chebyshev's inequality, and it shows explicitly how this depends on n, so that when you send n to infinity, this actually decays appropriately. Now, I want to mention but not prove the strong law of large numbers, which is analogous. Of course, it's going to be stronger, and the proof is subtler, but I want to talk about some heuristic arguments which justify why it might not be ridiculous to expect. So this is the strong law of large numbers. Just say QED here. Strong law large numbers. So this also holds, and it gives a stronger form of convergence. Convergence in measure, again, to reiterate, is quite weak, and in general, when you're dealing with things in analysis, many different conditions like pointwise convergence, which is relevant here, or pointwise almost everywhere convergence, implies convergence in measure, as does certain kinds of LP convergence, I believe, and you can work through the whole network of implications. There are many different forms of convergence, and their relationships can be quite subtle. So this states that Sn of x goes to 0 for almost every x, right? So all but null set. So the proof is subtle, and it would follow from argument for the weak law of large numbers if the harmonic series converged, right? But I want to emphasize that the sum, while it diverges, it does so incredibly slowly. And due to the growth rate of this function, or this series, it's not unreasonable to expect the strong law of large numbers to hold, right? The sum is barely infinite in some very loose sense. So if we pass to the subsequence, indexed by n of k equals k to the 1 plus alpha, where alpha is very small and positive, then we can make the following asymptotic estimate. I'll just play it fast and loose here. The sum of the reciprocals of this subsequence will be related as follows: 1 over k to the 1 plus alpha. And since the modulus of convergence here is 1, even if we add some very small alpha here, the sum is actually going to converge. So this is, so in particular, we have almost sure convergence. This is the same probabilistic language for almost everywhere, of the subsequence of Sn indexed by n of k, as above. And this technique is called sparsification, where you're passing the subsequence and you have almost your convergence when you pass to that. Now, here's a rough argument as to how you upgrade this in some way. So you can show or formalize that n of k, for any integers that lie between two elements of the subsequence, n of k plus 1, the values of Si of x are all almost the same with k sufficiently large. So once you're far enough along in the subsequence, k is large. Which means that convergence along the subsequence, as soon as you have the stability that's given by the fact that these Si are all almost the same when k is large, implies convergence of the whole subsequence. That is to say, pointwise almost everywhere, which is indeed the strong law of large numbers. So I know this isn't a mathematically acceptable proof, but it is a kind of gut instinct argument as to why it might be reasonable for it to hold, given the argument for the weak law of large numbers, which we have proved in detail. So hopefully this shows some interesting interplay between the different modes of convergence and probability theory by illustrating with a simple model of coin flips and how this matches up with our intuition or even supersedes it. And yeah, I might make more videos on analysis and probability in the future, so stay tuned for that. Otherwise, thank you for watching this.